Welcome to the first question. What exactly is DeepSeek AI, and what makes it stand out among recent developments in large language models? As researchers and engineers, understanding how DeepSeek breaks the mold with its architecture and training design is fundamental to appreciating its impact on AI scalability and reasoning capability. DeepSeek AI is a cutting-edge language model that leverages a sparse mixture-of-experts architecture with 671 billion parameters, yet activates only 37 billion parameters for each input token, dramatically reducing computational cost. It introduces multi-head latent attention, which enables processing of contexts as long as 128,000 tokens, and multi-token prediction for efficient generation. Together with a novel 4-stage reinforcement learning from human feedback pipeline, designed around group relative policy optimization, DeepSeek achieves reasoning performance comparable to leading models like GPT-4 while using approximately 98% less compute in training and inference. Next, we dive deeper into one of DeepSeek's core mechanisms. How does the mixture-of-experts system function? This is crucial for those seeking to understand how models scale without prohibitive cost increases. Within DeepSeek, the mixture-of-experts system contains 256 specialized subnetworks, or experts, in each transformer layer beyond the initial 3. For each token processed, only 8 experts are dynamically activated based on learned gating. This dynamic routing allows the model to scale its parameter count much larger than dense models, without a corresponding linear increase in compute or memory usage. The gating function learns during training to assign inputs to the most relevant experts, and load balancing mechanisms prevent certain experts from dominating. This sparse activation pattern enhances both efficiency and specialization, enabling very high capacity at practical cost. Attention mechanisms lie at the heart of transformer models, but DeepSeek innovates with a variant called multi-head latent attention, or MLA. What is MLA, and why is it so pivotal for long-context language understanding? MLA replaces the traditional quadratic scaling attention mechanism with a compressed, low-rank factorization of the key and value tensors. This compression enables handling sequences up to 128,000 tokens, far beyond typical transformers limited to a few thousand tokens, without incurring massive memory or compute costs. For example, this allows DeepSeek to answer questions about entire books or sprawling technical documents in one pass, maintaining context coherence and nuance previously unattainable. Autoregressive language models typically predict a single token at a time, but DeepSeek uses multi-token prediction. What does this mean, and how does it improve model performance and throughput? Multi-token prediction employs 2 parallel prediction heads in DeepSeek. One produces the primary token stream, while the other speculates on the next token. With acceptance rates around 85 to 90% for speculative tokens, the model confidently predicts multiple tokens per forward pass. This approach reduces latency by overlapping token predictions, crucial for real-time applications such as conversational AI or rapid code completion, where milliseconds matter. The training process of DeepSeek incorporates both supervised learning and reinforcement learning. What does this hybrid training pipeline look like, and how does RLHF fit in? DeepSeek's training progresses through 4 stages. First, a cold start supervised fine-tuning uses high-quality human or LLM-generated reasoning traces to establish solid language and reasoning grounding. Next, GRPO-based reinforcement learning optimizes the model for stepwise reasoning and coherence. The third stage injects vast synthetic training data with rejection sampling for quality control. Finally, a final RL stage aligns the model with diverse human preferences and ethical guidelines. This structured pipeline enables DeepSeek to develop advanced reasoning capabilities while balancing language fluency and alignment. Group Relative Policy Optimization, or GRPO, is central to DeepSeek's RLHF. How does this optimization differ from traditional PPO methods, and why is it better suited for large language models? In GRPO, instead of relying on a learned value function like PPO, a group of candidate responses for each prompt is generated. The advantage function is calculated relative to the group's average reward, stabilizing training and reducing variance. This method simplifies reinforcement learning for language generation by directly applying reward feedback without the complexity of value networks. It's particularly effective for handling large output spaces and supports complex reward engineering essential for reasoning tasks. DeepSeek's R10 approach uniquely achieves strong reasoning by purely reinforcement learning without initial supervised fine-tuning. What are the implications and challenges of such a method? By starting from the base model and optimizing purely through reward signals derived from self-play or automated judging mechanisms, R10 demonstrates emergent problem-solving abilities without any labeled reasoning examples. However, this approach may suffer from linguistic inconsistencies, including mixed languages or ungrammatical constructions, and requires careful reward optimization to ensure output quality. Despite challenges, it illustrates the potential for models to learn reasoning autonomously in unsupervised settings. Compute cost is a major factor limiting accessibility to large AI models. How does DeepSeek achieve such impressive cost efficiency compared to models like GPT-4? By activating a sparse subset of parameters through MO, compressing attention storage with MLA, and using multi-token prediction to increase throughput, DeepSeek dramatically reduces the required GPU hours for training and inference. Its training cost is conservatively estimated at approximately $5.58 million, a fraction compared to hundreds of millions typically reported for dense models at similar performance levels. This efficiency enables broader research participation and application deployment. Open-ended reasoning and self-correction are challenges for many language models. How does DeepSeek advance in these areas to generate more reliable outputs? DeepSeek incorporates reasoning step tags, enforces output structure with reward penalties for repetition, and optimizes for reasoning chain completeness. This promotes model behaviors where outputs include explicit reasoning trace steps, allowing validation mechanisms and iterative refinement, enhancing trustworthiness in complex, multi-step domains like mathematical problem solving or scientific research. Benchmarks validate real-world AI capabilities. On which benchmarks does DeepSeek excel, and how does it compare to other state-of-the-art models? DeepSeek meets or exceeds performance benchmarks like AIME 2024, 79.8% accuracy, Math 500, Codeforce's programming challenges, and GPQA Diamond Scientific QA, matching or surpassing leading models such as OpenAI's 011217 and Anthropic Claude. Notably, it achieves this with a significantly smaller number of active parameters, showcasing the effectiveness of its architecture and training. Multimodal reasoning integrates text and images. How does DeepSeek approach multimodal tasks within its architecture? DeepSeek VL2 extends the MO architecture with dynamic tiling vision encoders and multimodal fusion via MLA-enhanced cross-attention layers. This enables tasks such as optical character recognition, visual question answering, and spatial reasoning, providing competitive or superior performance compared to specialized vision language models, all while maintaining parameter and compute efficiency. Running advanced models efficiently in production requires technical know-how. What practical tips help deploy DeepSeek effectively? Deployments benefit from using BF16 or F8 precision formats, leveraging hardware like NVIDIA A100 or H100 GPUs, caching key and value tensors to handle 128K token contexts efficiently, monitoring expert activation for workload balancing, and carefully tuning reward models to optimize RLHF outcomes in target domains. Most real-world applications require domain adaptation. How can teams fine-tune or customize DeepSeek for specific use cases? Fine-tuning typically involves supervised training on domain-specific datasets followed by RLHF with bespoke reward models that encode domain expertise and preferences. The modular MO architecture supports efficient training by focusing updates on relevant experts and reducing catastrophic forgetting. Long context processing is vital for many applications. How does DeepSeek manage extremely long input sequences without loss of performance? The MLA mechanism compresses attention caches and, combined with the yarn memory extension technique, enables the model to retain and attend over 128,000 tokens with near-linear resource scaling. This capability supports demanding tasks such as legal document analysis and multi-file codebase comprehension where whole context understanding is essential. Community collaboration is key to advancing AI. Is DeepSeek available for open research, and how can researchers engage? Yes, DeepSeek offers open checkpoints, extensive training documentation, and modular codebases under research-friendly licenses. This facilitates reproducible experiments, custom extensions into new modalities, and cross-institutional benchmarking efforts, promoting transparency and rapid innovation. Deploying DeepSeek requires careful hardware choice. What hardware is recommended for efficiency and scalability? Modern GPUs supporting BF16 or F8 precision formats, such as NVIDIA A100 or H100, are optimal. The architecture supports expert sharding and memory-efficient context streaming, enabling deployment in both large-scale cloud setups and smaller data centers, balancing throughput and VRAM demands. Reward design strongly influences RL-trained model behavior. How does GRPO reward engineering shape DeepSeek's outputs? Using compositional rewards targeting accuracy, reasoning step fidelity, and output structure, GRPO encourages comprehensive, non-repetitive reasoning chains. Careful reward scaling prevents mode collapse and promotes exploration, balancing fine-grained logical consistency with broad adaptability. No AI model is perfect. What are some current limitations and research challenges facing DeepSeek? Challenges include linguistic inconsistency, especially in pure RL models, difficulties in tightly fusing text and vision modalities, persisting hallucination risks, and the need for better grounding mechanisms. Ongoing work focuses on refining reward models, integrating external knowledge bases, and developing hybrid architectures. Artificial general intelligence remains the goal of AI research. How does DeepSeek contribute to the AGI field? By demonstrating emergent, multi-step reasoning in a scalable, sparse expert system trained with human-aligned reinforcement learning, DeepSeek bridges narrow LLM capabilities with AGI-like generalization. Its transparent reasoning paths support interpretability and safety, key pillars for future autonomous AI systems. Finally, what does the future hold for DeepSeek and the broader family of similar models? Future directions include adaptive expert routing, richer reward compositions, multimodal and multi-agent reasoning expansions, and broader integration into real-world pipelines. Open-source collaboration will accelerate advances in alignment, safety, and general problem-solving capabilities toward practical, safe AGI.